Thank you for coming for Hack in the Box 2018 and for this talk. My name is Ofir Arkin. I'm the VP of Security at Mellanox, which means that I'm responsible for security technologies in our products. And today I'm going to speak about SmartNICs and how we can use SmartNICs in order to provide with far better security in the data center. So how many of you know network interface cards, SmartNICs, this type of stuff? Not a lot? Okay, cool. We will define SmartNICs too. So let's start. I'll try to make for the time that we lost. Security in the modern data center suffers from various issues. Some of them are the responsibility of the security model. Some of them are the responsibility of the changes in the modern data center security, modern data center architecture. We'll talk about those. And then we'll go into understanding what are the issues that networking has in that environment, security has in that environment, how we can solve that. If we look at the traditional problems, it's kind of still amazes me that in 2018 I still need to mention the broken perimeter security model. You'll be surprised how many companies are still dealing with that problem. One of the issues for security is the inability of a lot of companies to change from what they have. So you know that you need to get into a new technology, but your networking environment can change, or the way that you have laid out your network can change, and you're bound to what you have and you need to deal with that. In some cases, we still see a lot of companies still have a lot of their security controls deployed at the perimeter only to be bypassed. There are plenty of examples that I don't need to repeat that showcases that. And like the medieval castle, that was a great place, a great security type of a place, only to be dismissed by gunpowder, by technology advances. So does the perimeter-centric security model, which was good for a while, and we'll see later on for how much while that was completely broken and needs to be replaced. The fact is that we used to trust people once they were okay to get into the data center, which created another problem due to the fact that they were able to go east-west laterally inside the data center as they may. We know that this basically created interesting situations in which an attacker that had to be right once in order to get a beachhead in the data center could then use that in order to gather and amass other systems inside that data center, due to the fact that literally not a lot of data centers had the type of controls inside a data center that would allow them to have the visibility into what's happening inside the data center. So you look at this and you ask yourself, okay, is that a problem that we had 10 years ago, and is this a problem that we have now? Yes, the same thing. We have a complete lack of visibility problem today, and 10 years ago, pretty much the same. A lot of companies, organizations don't know what happens in their own data centers. Attack sophistication, I think everybody agrees to that, right? So we don't need to talk about that a lot. In many cases, attacks are not that sophisticated and still they do what they need to do. Complexity is an interesting thing. And I want to read you a paragraph that is a quote from Rob Joyce. Rob Joyce used to be the head of TAO over at the NSA. These are the guys that are responsible for nation-state hacking, for those of you that don't know. And he said in a public appearance, I think a lot of people think the nation-states, they're running on this engine of 0 days. You go out with your master skeleton key and unlock the door and you're in. It's not that. Take these big corporate networks, these large networks, any large network, I will tell you that persistence and focus will get you in. will achieve that exploitation without the 0 days. I think this is a great quote, because it shows that the fact that we have complex software and network really allows others to get into the network and not the 0 days. Sure, the 0 days are helpful, but eventually the fact that networking is complex and software is complex has a way to expand the attack vector, and we'll show an example coming in a few slides. Geopolitical. So the Snowden effect over privacy, meaning that a lot of the traffic today, literally any known site today on the internet is encrypting its traffic. This also causing disruption to those security solutions that had to look into the traffic and make some conclusions about what's happening. Those tools are turning dark because we're using encryption more and more. This is also true to traffic inside the data center. So east-west traffic, there's a lot of people that are now starting to encrypt that traffic as well. This is also good if someone is able to get access to your networking gear, looking into the recent news about that manufacturer and the problems with their switches. Geopolitical also means that everybody literally hacks everyone. So it's not just one nation state that hacks another nation state, it's every nation state hack every nation state. And way that we use to basically put lines between this country or that country, these lines are gone. So enterprises today basically deal not just with criminals, they also deal with nation states if they want it or not. I think another point that is worth mentioning is the fact that a lot of enterprises are actually dealing with what I'm calling yesteryear's problem. In technology, when we have new technology and want to deploy it, we think that the technology we have fixes the most important problems that an organization may have. But in reality, we sometimes find out that organizations actually have problems that we thought that are long had been resolved, right? This morning, people talked about patching, this type of stuff, but it's much more harder to actually do these things rather than people actually think on a large scale. The other interesting things that happen is the fact that the data center is not what it used to be. The data center was the most static place in our organization, in any organization, and now it's one of the most dynamic places that we have. The number one factor that caused this change is the fact that we now have modern application architectures. So from building those beautiful monolithic things, if you remember 20 years ago, it was just we built a box, we put it on a box, and we were done with it. We now build applications that are multi-tiered, they are distributed, they're independent from a specific server, and they're elastic. So in their nature, they can grow and shrink, right? And this, in turn, created a massive shift in the ratio between the east-west to north-south network traffic. So if in the past, the external traffic was 80% of the total data center traffic, now 80% of the traffic is traffic inside the data center. This, in turn, had to inflect change on the networking equipment and on the architecture that we're using. So the fact that we're using ultra-fast, low-latency top-of-rack switches, the fact that now a lot of the intelligence and forwarding decisions are being made inside the servers themselves, and also the fact that we have moved to a 1 or 2 tier leaf and spine network architecture, that the idea there is to have the same bandwidth and latency from any server to any server, since they are in equal distance between each other. So basically it means that you can deploy your application the way you like without any need to take into account the data center topology. So all of these changes are connected to each other The second most important change is virtualization. A lot of people don't think about how much virtualization changed the way that we do things in the data center, but virtualization did the biggest thing for the data center, maybe for security. It extended networking into the host, right? These virtual machines needs to communicate between themselves and to the outer world, and we had to have a switch, right, in order to allow to do that. And later came the virtual router, the virtual load balancer, and the virtual whatever you want, basically in software inside a host. And suddenly, we married between infrastructure capabilities, right, to user applications. They now are found on the same box, and we'll talk about why it's so bad. The other thing that virtualization did is basically it commingled applications, different applications on the same host. It created a dynamic way that virtual machines pop and are being deleted all around the data center. So it created a sense of provided a dynamic nature to the data center. Not to mention that it also helped in doing far better scaling and supported the model of software-defined networking, where in virtualization, when you look at virtual switching, you have a control plane and you have a data plane. The policy is in the control plane, and the data plane actually acts according to what the control plane tells it to do. The control plane gets this policy from the controller, and that's literally a host-based SDN type of a model. The last one is extremely important, and a lot of people tend to forget that. I assume that most of you come from an enterprise and not from a cloud provider. You're on 10 gig, maybe the more advanced guys are on 25 gig. But as the network traffic goes up, the software isn't capable of keeping up. So if you've been at 10 gig and you've been able to squeeze your precious CPUs, maybe I'll give it to you. But at 25 gig, you can forget about it. Software alone is not going to help you. You're not going to be able to process that data, period. And that creates other interesting issues that we'll talk about later. So what have we done? We looked at that problem, right? And we decided, as far as a strategy, to take security and push it into the data center. And we said, okay, the community, the world, the strategy that was taken was same as virtual networking, right? We will push security to the server access layer as virtual networking. We'll treat it as a software-based SDN. And actually, the server access layer is the only place on the network, if you can think about it, that you'll be able to have granular visibility and control over any type of a workload. Why? Because it's the point where the traffic is going to get encapsulated or decapsulated depending on what you're using. So if you're using virtual networking, that is going to be the point where VXLAN, Geneve, and other lovely tunnel protocols will be used. And if you're using security, that might be the only place where you will be able to see the traffic before it's encrypted, decrypted. Where I like to say that the network is getting dumber and the host is getting smarter. If you play this back 20 years back, 15 years back, even 10 years back, that was completely opposite. We used to do everything on the network and nothing at the server access layer. Today, we're doing the opposite. Everything is done on the host and nothing on the network. Say nothing is not totally accurate. You still do stuff, but the heavy processing is done on the host. The other thing that was born out of virtualization is all the notion of microsegmentation, the idea that applications needs to be secured per application. So those applications needs to be isolated from each other, and every tier needs to be segmented, so only services that are needed by the application in order to run are allowed. and the security controls needs to be applied according to the risk factors of each of those workloads. That's why whoever, as a commercial company, has a good controller that is able to properly automate and orchestrate the policy, which now becomes the most important thing in controlling all of this, has a product that is being sold very nicely. All in all, pushing everything into the host creates massive scalability because the network becomes much more simpler and you can scale it as well. So you disconnect from the scaling perspective the compute from the networking, and you can actually go and scale very nicely here. So up until here, pretty much, I assume everybody are good. No questions? Too much food? No? We're all good? Okay, cool. So what are the problems? So it's not just all nice. The problems are starting from performance. When you, in the past, had your entire server for yourself, you had all those precious cores to yourself. So you can just use them and just run your applications, everybody were happy. When we pushed virtual networking into the host, we took away some of those precious cores. A lot of the organizations that I'm dealing with actually paying anything between 40 to 60% of their cores to run virtual networking. 40 to 60%. Okay? So if you think about it, you need to match between what your virtual switch needs in order of throughput and CPU with the VMs that are being deployed and the containers that are being deployed with, again, their throughput and CPU needs. And you need to get to an equilibrium. If not, then there's going to be a bottleneck between the two. The other thing is that when you start pushing security into the edge, since now we're doing IPsec between different parts of the applications, or even terminating TLS down at the VM level, you're using anything between 8 to 12 cores if you're looking at IPsec at 40 gig. So technically speaking, you're not left with any cores to run anything. So you ask yourself why people don't use encryption. They don't use encryption because it kills their applications. It kills the power that they have on that server, even when they're using the ASNI instruction set. Okay? And that's the most important problem that we're seeing here. The other thing here is, when I mentioned earlier on, is the software efficiency. That's exactly what you get. You get to a point where you can't run at these speeds without any hardware acceleration. And that's a very important thing. The other issue is related to security. So I mentioned earlier on that this is the first time that knowingly we are commingling infrastructure with user applications. Okay? And this is the worst nightmare for security that anyone can think of, because looking at the history of how you do security in the data center, you want to disconnect between the two, right? You want to make sure that your infrastructure is being dealt separately from your compute, from applications. So think about providers, right? Any IaaS provider, and even your own infrastructure. And how many of you know Open Virtual Switching? OVS? Okay, cool. So in this scenario, OVS runs within the hypervisor. This is very common. Take KVM, for example, and OVS. The control part, where the policy and the decision-making about how to handle traffic usually runs in user space with root privileges. And the data path runs as a kernel model. Now, how can I take this and influence the way that these things operate? So CVE 2016-2074 is a buffer overflow against vSwitch-D when parsing MPLS traffic. So how this actually works You have traffic that comes in from the virtual machine. The data path, we look into its flow tables. We look whether there is a policy match to match this traffic, right? The way that it will do that, it will parse the headers of the packet versus the policy that it has. And if there's no match, what it will do, it will forward the traffic to the control plane, to vSwitch-D that previously would load the policy that was pushed into the OVS DB server. And what vSwitch-D will do, it will parse again the headers, will match it with the policy, and will make a policy decision as far as what to do with this traffic. So what the guys that uncovers that found out is that when they played with the way that the MPLS header was parsed by vSwitch-D, they created a buffer overflow. And the buffer overflow, basically, the end result was a root shell on this side and the hypervisor. That's cool, right? So I'm sitting as a user, and now I have a root access to the hypervisor, which basically means that I compromise the entire server. But it's actually more than that. It's even much more problematic. So this is an architecture of a modern data center. You can see the leaf and spine switches and how this is connected to the outside world. And traditionally, what we've done, we have separated between the networking infrastructure to the compute to the management network. So the management network, when we used to talk about management network 10 years ago, we were talking about the network that manages the switches and the routers, right? And now we extended networking into the host, and suddenly our controllers, take OpenStack for example, needs access to both switches and compute because they configured them according to your deployment. So all of this becomes one happy mesh. And what you can now do, you can get access to one of those machines, either by renting time or by hacking application. And if you compromise that virtual switch, you're not able to talk to the controller because that controller also is able to talk to your box because it pushes policy, and in some cases it handles stuff that the local control plane doesn't know what to do with. So the guys that discovered that buffer overflow, what they've done, they've installed one of the commercial controllers, and then have done the same thing to the controller. Since the controller had an instance of OVS as well, they basically, since the traffic from the compute to the controller is allowed, they send it an MPLS packet, got a root shell on the controller, and that's an end game. Basically, they got access to the entire thing. They control the entire infrastructure because now everything is connected, and you basically take control of everything. So what is this telling us? This telling us is that in this model of this new brave world of software-defined networking, we're being told that our security depends on host-based security. But isn't host-based security being a failure for the past 30 years? Now, when I put this, I didn't know if I want to talk about this. Seriously. And I remember the ping pong virus. I know some of you may have not been born then. Yeah, I know I take the age average here to tops. But it was actually fun. You take a 5-inch your floppy disk, push it into your PC, and you saw this stupid ping pong ball jumping, and you're like, wow, I got a virus. You know, that was the reaction that people had 30 years ago. It's 30 years. The ping pong virus spread without people being connected to the internet, guys. You get what I'm saying? Nobody was connected to the internet, and yet we all were affected. The other interesting thing that happened in '98 is the Morris worm, which was much more interesting to the world than the ping pong virus. I tried to differentiate between technology and events to issues with security. So Windows 95 was an amazing event for connecting people to the internet. The first time that a real graphic OS was working, not like Windows 3.1. If some of you remember how you used to switch to DOS and come back. I'm saying DOS, people look at me, what the hell is that? It was extremely significant, albeit the fact you connected your OS without any defenses to the internet. And then Windows 98 came in '99, and basically software security went mainstream, yada, 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 back to the Meltdown and Spectre instances that showed us that regardless of what we do, CPU is not our friend, and not just the software. And basically, when I look at this, with every technology advancement that we made in the past 30 years, came issues with our technologies, and again, another chapter and another chapter, and it's an endless type of events. Any questions on this? You like this? Yeah. It's kind of funny to look at what at the end, and there were other things here. A friend of mine reminded me how we watched The Cult of the Dead Cow back in 2001 showing bad orifice, where basically the idea was, hey, I can open up a link from inside the network and nobody filters me. Wow, great. If you didn't do two-way type of firewall, that's what you had to do. But that was the first time that people showed a tool with a GUI, with a plugin system that allowed people that didn't know a lot to actually hack into places and showed how security was faulty. So that was 2000, 2001. There are other interesting things happening here. So we know the end result, right? What will happen? And that brings us into SmartNICs. So a lot of people ask me, what is a SmartNIC? Right? People know a network interface card. That's the card you shove in the server, and it provides connectivity. But actually, it provides much more things. It's much more smarter than that. It has hardware engines that accelerates different functions. It makes networking runs much more smoother. It makes some of the programs that you run on your machines actually execute at the network speed that they should. It offloads precious CPUs. That's a regular NIC. But a SmartNIC is actually a computer. Why? Because if you look at the components, it has a CPU, it has cache, it has those hardware-based accelerators, it has a full-blown OS, usually Linux, and it has all the goodies that that network adapter also had. So instead of just having a data plane, now you can actually have a data plane and a control plane together. And that brings some really, really interesting things that can be done. Now, the one thing that we all need to remember, this is not an x86 architecture where you don't care about power, right? You take an x86 CPU, you plug it to the power plant, and everybody are happy. This is limited. This is limited by 35, 40 watts tops, okay? So the deal here is also to combine all of those components so they work in concert. And that's really what makes a SmartNIC, because if you just, take it and do it-yourself HomeKit type of thing, it's not going to work because it's not going to be efficient. You have to make sure that the interfaces between CPU, memory, network interface card, cache, all of that works as they need to work in order for this thing to be efficient. Now, there's a lot of hype in the industry. A lot of people call some stuff, SmartNICs, but at the end of the day, if you don't have a CPU attached to a network interface card, that's not a SmartNIC. Okay? So why is this interesting? Why is this thing that has a CPU now becomes an interesting thing? It becomes an interesting thing because we can use it to isolate functionality. So traditionally, we would run Open Virtual Switch on the host, right? And it will be exposed to a plethora of issues. What we can actually do with the SmartNIC, we can take the data plane that I showed you that in some cases implemented as a kernel module and run it and accelerate it on the data plane that this card has. Take the control plane that runs in the hypervisor and user space and run it over the operating system that runs on the CPUs here. And basically what you do by that, you take a function, an infrastructure function, and you completely implement and offload it from the x86. So what happens is that the x86 suddenly don't have access to that infrastructure function. It just gets interfaces, that's all. It doesn't have any way to play with that function or to influence anything because, as I'll show you, what you do is you isolate the x86 from the SmartNIC. And you let the SmartNIC run as a computer in front of a computer. And those infrastructure functions can be networking, can be storage, and can be security. Because you can accelerate, for example, IPsec on the data plane and handle any exceptions on the control plane. I'll show you some examples that will be much more illustrated. Any questions about this? Yes?
Just to make sure that we're talking about the same stuff. You know the net FPGA?
I know FPGAs, yes.
Yeah, so is there a difference between SmartNIC and FPGA? In essence, an FPGA-based card
FPGA basically replaces or adds data plane functionality. So you use an FPGA usually to accelerate the function. You don't have a CPU. It's not true, but some FPGAs have ARM CPUs with them that do certain things, and then you can call them a SmartNIC. But most of the FPGAs today, they are a marriage between a network interface card and an FPGA without any CPU whatsoever.
Essentially, the difference is that SmartNICs really run on a small operating system.
The difference is that the SmartNIC has also CPUs that when you want to, that those CPUs can actually control what happens on the data plane without the need of any intervention from the x86. So you can, and there is an example coming, you can have the same flow that I showed earlier on with OVS. A packet comes into the NIC. The NIC doesn't know what to do with it. And instead of sending it to the OVS in the x86, you send it to the OVS in the OS, the Linux OS that will be running on those CPUs. That Linux OS, that component will be the policy decision point, and everything will be compound to that component. So no need to ask the x86 to intervene, or no need to use anything else in order to make those decisions and to control how the packets will be processed. Make sense? Okay. Anyone else? Okay. So I'll try to do this slowly. There's a lot of stuff here. Spend a lot of time on how not to do this slide right. So trying to make sure that everybody follows. So the first important thing is to remember that this SmartNIC usually uses SRIOV. So what is SRIOV? How many of you are familiar with it? Okay, 2 people. So SRIOV pretty much allows multiple different guest machines to use or to share a single physical PCI device. It also bypasses the hypervisor. So what happens, the network traffic or the guest machines actually gets access directly to hardware. The traffic from those guest machines do not pass the hypervisor kernel or the hypervisor at all. It goes directly to the hardware. And what that hardware does, it provides data protection between those two different virtual machines. So now you can think on how this might be used for example, for a layer 4 firewall or for workload-based policies. And SRIOV allows us to treat a VM per VM as an instance by itself. The other interesting thing is that it provides a near bare metal performance. When I say near bare metal, you're talking about near bare metal. For example, if you look at the NIC that has a 40 gig, you'll get 39.5 or something like that, other than a 40. So this really is the most fastest way for you to provide networking to a guest machine. Other important functions. So in SRIOV, you have physical functions that are managing multiple virtual functions. The virtual functions are those that are eventually connected to virtual machines, and the physical functions are those that manage them and manage the virtualization. But really what's important here is that the Uber commander for all of that is the driver. Okay? What's the difference here? The difference here is that in a regular NIC, the commander will be this driver that sits in the hypervisor. In a SmartNIC, you can't allow it to happen if you want to use the SmartNIC for security. And then you have a special driver here that eventually manages this guy and manages all the SRIOV functions. The other interesting thing, when you think about it, is that when you receive packets here to the NIC has to implement at least a layer 2 switch in order to be able to switch the packets to where they need to go, right? Now the SmartNIC has the ability to control the guest machines per guest machine, and it needs to be able to switch the packets to the right virtual machine after it passed whatever policy it had to be applied to. And by doing that, there is a logic here that we'll talk about in a second that basically the packet goes through, that classifies the packet, compares it to the policy implemented, and basically according to what is implemented, that would determine the path the packet will take. Okay? Questions? And again, whoever controls that is that driver. So you can see that all the functionality, whether for this embedded switch or whether for this SRIOV, are controlled by a driver, and the driver sits on the ARM side. Okay? So traditionally, that would be the driver sitting on the x86. On the SmartNIC, it will sit on the ARM side. What else? As I said, control plane will be implemented here. Data plane will be implemented here. There will be actual PCI switch implemented in the SmartNIC that will prevent this guy here from accessing this guy here. So it's a physical hardware switch that prevents any traffic from going that way. Other interesting line items, since the SmartNIC has its own memory, it will use it. And as I said, it's able to provide a workload by workload type of functionality. And some of those will also do secure boot, which is starting to be a very much important line item when you look at network interface cards as is. What will happen, and I'll show you how it's done. The SmartNIC CPU, as I just alluded, controls everything that happens on the NIC side. So any type of operation that we want to engage with, the CPU here controls it. It's also isolated from the host and from the production network and somewhat from the NIC itself. And in some cases, you'll also find a dedicated network interface. So all of this design basically is tailored towards making sure that this part continues to be independent in its operation and controls the NIC side, and taking away any functionality whatsoever that the x86 had controlling how SRIOV or the embedded switch operates. Okay, any questions on that? I know it's a lot of material, very fast, but okay. So the way a policy will be implemented in that switch, it will be like if you know OpenFlow. It will be a series of match action tables. Each one of them is a flow table. Some people like to dedicate a table pair a function. It's easy to explain how it's done this way, but usually when you're in a data center, you want to make sure that the traffic that you're getting, actually you need to get it. That's the access control. Then you want to make sure that you are terminating virtual networking. So VXLAN traffic, with Genève traffic, whatever will follow, which means it will be a series of matches. And usually you'll pop the VXLAN header, you'll take it off, and then the packet will go through whatever other policies are implemented for it, and providers as well as enterprises use this in order to terminate their virtual switching, implement security, do encryption, and do load balancing and other stuff. So anything that you can actually do in Open vSwitch, for example, in software, you're able to implement in silicon, grosso modo. So if we look at this again, we now can actually look at that as a model for policy and policy enforcement. So the NIC side, the embedded switch, will be a policy enforcement point. Traffic will come into the NIC side. We will look for a match to what to do with these packets. If we will not find a match, then we will be consulting with the policy decision point that exists here in the vSwitch D. That's the example that I'm using. And we will also be able to introduce additional software that will run on those CPUs that will provide additional policy enforcement. So this is not just bound to Open vSwitch or to this thing or another. You can actually extend the type of functionality that you want to provide and link with other applications that you want to have. The reason I'm using OVS as an example is because it's mostly known and people know about it, so it's easy to explain what is done here. So in order to better illustrate this, and I'll come back to this example in a second because it's important. Packet comes in. There's no match in the flow tables. Exception sends it to the ARM side. The ARM side will make a decision what to do with this based on the policy that is implemented in OVS. It will match it with the classification of the packet. If it decides that this traffic is allowed, it will push a rule into the silicon here and into the data path part of OVS that would basically say, hey, for this classification of the packet, allow this traffic. And from now on, this traffic will go through the data plane, connected directly to the virtual machine without interference of any software whatsoever. So by doing that, what we've done, we've first offloaded all the traffic to the data plane. We used the policy to determine what to do with this traffic, and we made sure that silicon, at the end of the day, deals with that, so it gives it a line rate type of operation. You had a question?
I was wondering if you could still exploit the OVS part. Let's hypothetically say that's possible. You could still do a DMA tag since you then have access to the PCI bus. You can do a DMA tag and gain control over the hypervisor.
Don't forget that you don't have any access from the x86 down to the ARM side. No control whatsoever. So it's enforced. You may try, but it's enforced by hardware and by access lists. So even if you try to have a reverse shell and assuming that the software will be exploitable, it will be blocked, and it will be far easy to detect that you are trying to do something with that. You're absolutely right. But your ability to actually take action against it is going to be absolutely zero. Coming back to this, so what I showed earlier on was that a single packet went here, a decision was made what to do with that packet, and basically the rest of the traffic went on. But you can think about other type of applications that you can implement using this. So how many of you did application recognition? DPI? No one? Okay, so for determining what type of traffic and what type of protocol is really actually going over here, you usually need 1 to 5 packets of the initial communication after the session has been set up. So instead of sending inserting the rule into silicon after the first packet, you let the session to open up. You'll send the traffic to an application here. Once the application will signal that it's done processing the packets and it knows what the protocol is, then you'll make a decision whether or not to continue and allow the traffic. Just one example. You can easily use this in order to do unaware IPsec, for example. What does it mean? It means that if an IPsec traffic needs to leave from those virtual machines and you don't want to set up the applications, you'll set up a policy here that says, hey, once you see traffic going from these guys targeting those guys, encrypt them in IPsec tunnels, and what you'll do, you'll use the CPUs here and the fact that you're running Linux to set up those tunnels, and you'll run IPsec in unaware mode, which means that the applications would not be aware that they had been inserted into a secure tunnel, and it just works. There are other examples here. You can decide that you want to run all traffic through a program here. You can still do it. So the ways that you implement your enforcement capabilities varies from one application to the other, or from what you really want to do to another. But really what you can get to is a very sophisticated way to implement any type of an application with connection to any type of an acceleration in hardware. I did a disservice to the hardware accelerators because the whole idea here is that the CPU that you may find on a SmartNIC is usually going to be an ARM-based CPU, right? It's not going to be as fast as an x86, and you're not going to crypto mine, currency here, right? Good luck with that, by the way. It's going to take forever. But what you want to do is you want to accelerate functions so this whole interaction will work faster. So if you are receiving traffic and if you are having some sort of a chain of services that you had built and you want to run on that CPU side, what you want to do is you want to use as much as acceleration in hardware that you may able to in order to basically save you the CPU even when it's run on the SmartNIC. So in that case, the example I gave on the IPsec in an unaware mode, examples for firewalling, and other examples that I'll be showing in a second, also gives you the ability to run very interesting applications here, and I'm about to just to show you some of them. Any questions on this? Okay. So the stuff that is most understood, I assume, is the fact that we can harvest telemetry out of the traffic. The SmartNIC is a bump on a wire. You see the traffic that comes into the host. You see the traffic that goes out to the host. Your determination point of that traffic using SRIOV, so you know that whatever you're getting is the traffic that is actually getting into those machines and getting out of those machines. And you have that visibility before the traffic gets encapsulated and decapsulated. Second, you can use that visibility, or you can just use policy to do microsegmentation. So applying firewall rules to segment between a workload to a workload, and eventually between one application to another. Just showed you how you can use OVS to actually do this. Done. Data in motion and data at rest. Mentioned IPsec and accelerating IPsec alongside running its control plane over the CPU part, and that allows you actually to do encryption east-west inside the data center, using these in order to better protect the traffic. There are also accelerations that some allow you to accelerate the encryption of data at rest, so it ticks another box. The coolest thing is to actually combine between encryption and microsegmentation. So you create rules of whom you allow to encrypt traffic to, and basically if traffic is not encrypted, it's also not accepted, and basically what you've done is you allow traffic between the different application parts just encrypted and automatically segment the network as well. The cool thing here, by the way, is that you don't need to change the network at all, because as a presence point, that SmartNIC can provide you with microsegmentation without the need to re-subnet the network, etc., because the policy is being implemented on the NIC itself, on the SmartNIC itself, regardless of what you decide to do with your networking. So underlay, overlay, doesn't matter. You can just enforce it, and that's a huge plus. The no need to change anything. The last thing is something that my team had been working on for the past year, and that's credit for Jack Matheson and Ahmed Atamla, who are the ones who play with this. So I had an idea. Usually when I have an idea, it's bad, meaning other people need to go and see that it actually can be done. But laughs aside, what I wanted to do is I wanted to create a way to query the host memory from this SmartNIC, bypassing software completely. So if you look at the use cases here, there is no intervention of the x86 in any of these operations whatsoever. x86 doesn't play any part. It just runs from the SmartNIC. SmartNIC does everything, gets policy from a controller, and basically does everything. And when you look at security, the flow-based part, the network part, is only one thing. You want also to get to a point where you are able to control the integrity of, or to be able to understand that the integrity of the machine had been compromised. So what we've done, I'll show you an early demo of that. We've been able to access the physical memory bypassing the IOMMU. So we are basically able to go to physical memory directly and kiss goodbye the IOMMU protection. Plus, if you don't know that, IOMMU, the TPT tables are software maintained. So if someone wants to hide himself, they can. So I'll show you a demo. I hope you like it. If I find where I put it. So what you're going to see here, you're not seeing it, okay. Let me find out how you're going to see it. Okay. It's going to be interesting to find out how to move this to, okay. So on the left side, you're going to see a program working on the CPU side of the card. On the right side, you're going to see the host. The host is going to pull an image, and you're going to see it on the left side pulled from a physical address. Okay? So this is the ARM side. And this is the x86 side, and what we're going to do, we're going to pull an image. It's going to be a bit small. And what you're going to see is that here on the right, We're gonna upload the image, and you'll see them both, and you'll see that the addresses that we show are the virtual and physical addresses, but we pulled it from the physical address below. Now, the application for this thing basically would enable us to do live forensics. That's the idea. So the idea here is to take this, and what we found doing this is basically that the tools that we have today, open source, are useless to what we're trying to pull here, because we are trying to just digest parts of the memory and using those parts of the memory to actually find where the rest of the stuff is, if you get what I'm saying. And once you get this mapping from the physical memory, completely from the physical memory, nobody can thwart the information that you're getting. And that's the killer thing here, because anything that we do today acquiring memory using IOMMU is software influenced, because those tables are being maintained by software, by a hypervisor, by the OS. So if I'm malware and I want to hide myself, I just go and change the tables. And here what we've done is basically we went and created a way to bypass this whole thing and access the physical memory directly. So what we're doing is secure memory-to-memory access from the CPU side of the SmartNIC to the host memory, and we're dumping only chunks of memory that would allow us to map the entire, the whereabouts, you should say, of the VMs, containers, and what the hell that runs there. So I'm left with 3 minutes and 30. I thought I would be done by 20 minutes, okay? Yes.
So this is exactly what I was trying to refer to. Once you can compromise the ARM side, you could be modifying the memory of the x86 side.
The protections that you are gonna have there are much more significant than just going to allow you to compromise that side. But you're right. Technically, on paper, you can use the data plane in the same manner to do this type of things. But the fact that this runs as an embedded device, and you know the boundaries, and you have means to isolate it, not just from the x86 talking to it, but also from it talking to the x86, allows you to detect issues that may occur there. Now, nobody says that we're gonna run OVS there, or we're gonna run this thing or another. It's just as an example. The idea here is just to show that the type of exploits that you've been running on the x86, and the fact that you can completely hide them, is going to reduce your exposure by a mile. It's not the same thing as running it from the x86, and it's also going to allow you to take the infrastructure functions and separate them from the applications, which is something that a lot of people that forget that the device that I showed that sends MPLS packet probably shouldn't be sending any MPLS type of traffic to the virtual switch. So it's also understanding what you're running against and how those systems behave, and what we're trying to pull here is not just the networking part, it's also the behavior part, which I think is much more significant compared to anything else here. There's also, what should you run, what tools should you execute, and if you're executing crap, then what I just showed you will get you as well. So the idea here is to make sure that we have all the right engines, right, to have someone use them in order to have an early detection that someone is actually playing tricks from the VM side or the container side down to the infrastructure side. Make sense? Yeah. Anyone else?
Yeah. Just a short question. If nobody, then we're going to move on to the next speaker. Okay, give a hand for Ofir. Thank you very much.
Thank you.